just to let everybody know we're a little bit better. Yeah. But we should make a t-shirt. I do want to do that. Okay. All right. So let's review just a little bit. And let's take the derivative of these four right here. So not integrating yet, just taking the derivative. All right. So I'm gonna freeze my screen while I work these out so that you can't see what I'm doing. I want you guys to try them on your own. Subtraction. Yeah, that's subtraction. It looks kind of like multiplication, but it's subtraction. Three, there are two ways you can do number three. For number three, you can use a quotient rule if you would like. If you do, your work will be different than mine, but you should still get the same answer in the end. Or I used a chain rule for this since I only had a 1 in the numerator. So I wrote this as 3x squared minus 4x to the negative 1 power. And so to take the derivative of this, it's very similar to number 1. You multiply out front by the negative 1. You decrease your exponent by 1. And then you multiply by the derivative of the inside, which is 6x minus 4. It is important right here that you have parentheses around that 6x minus 4. Because if you do not, then it's only multiplying this other stuff by 6x and then subtracting 4 on the end. So you do want parentheses around that. And then I moved the 3x squared minus 4x to the negative second. I moved it back down to the bottom. I just left this negative 1 out front as a negative out front. You could distribute it to the 6x minus 4 and get negative 6x plus 4. Just depends on how they leave it.
I think the top negative 6x plus 4 and then the bottom is 3x to the 4 times 4x to the third.
No.
Oh, Dickens.
It's not. You did something wrong on that bottom part.
Okay.
whenever you do that quotient rule, it should just be the denominator squared, right?
Yeah, I did that, but then I didn't do that.
Yeah. Okay. All right, questions on that one? The last one's not really a chain rule. You could do it with a quotient rule if you want. I guess you could kind of do it with a chain rule if you want to have like an x to the third inside of that square root. But the best thing to do is make it negative exponents. So you got x to the negative 3/2. And then how many of you at first got an answer that had an x to the negative 1/2? Like you integrated it instead, or was it just Troy? I also, nobody else is admitting it, Troy. I also started to integrate whenever I did this problem. I caught myself and erased it, but I started to integrate. But you are multiplying out front by the negative 3/2, decreasing your exponent by 1, because you're taking the derivative here, not integrating. It's the curse of integration. Like when you learn how to integrate, what used to be really easy to you in taking a derivative, sometimes you do wrong because you just mix up and do the wrong thing now. But and then whenever you do this, you can send that x to the 5/2 back down to the bottom, which can be written as square root of x to the 5th. Okay, questions? Probably good that we had a little bit of a refresher on some derivatives. I think we're probably doesn't hurt to practice that a little bit because we're forgetting a little bit of it. So what we're learning today is how we're going to undo some of these things that we've done here, right? So here is our rule that we are going to use. I'll let you copy it down and then we'll talk. The calculus wrap. I do not. Maybe I need to grade a little harder. Maybe not put an AP curve on one of the tests so that you have to make a wrap live to salvage your grade. All right. Okay, so these two lines right here are just two different ways of writing the same rule. So what we'll be looking at here is we're trying to integrate a composite function. So we have a f of g of x. In order for us to integrate this, to kind of go backwards from the chain rule, there will have to be the g prime of x right here. Okay? So we will have f of g of x times g prime of x. And then when we integrate that, when we go backwards, it will give us capital F of g of x. Okay? This also could be written with, really I prefer this notation here, and not just because it's the FU right there. But the u, it sort of simplifies it here. U can be your inside function, right? And du is that derivative of that inside function. It's going to be a little bit easier for us to use this second notation right here. Okay? So, let's look at this first problem and see how this is going to be used. So, what we're looking for here is we need to identify what was our inside function part, what was our outside, and what was our derivative of our inside. Okay? We call the inside, we're going to call the inside part u, and we call the derivative of the inside du. So you can kind of see here, you have this stuff right here being raised to a power. So here, that x squared plus 1, that's going to be your u. Okay? So u equals x squared plus 1. Okay? So if I take the derivative of that, right? If I take the derivative of x squared plus 1, I will get du over dx equals 2x. Now, I don't really want du over dx. I just want du for that. So I could multiply both sides by the dx. So du equals 2x times dx. Okay. Now, for us to integrate, our du needs to be in the problem. And fortunately for this, because this is our first problem and it's going to be the easiest one that we do probably, that's already here, right? I've got 2x times dx. That is my du. Okay, so this is called integration by substitution. Sometimes you'll just call it like u or u. You'll call it u substitution or u du substitution for this. So what we're going to do is we are going to rewrite this equation right here with u's instead of x's. So I'm going to rewrite this as the integral of all this stuff on the inside, 2x squared plus 1. I'm just going to call that u, and it's being raised to the second power, so it's u squared. And then all this stuff I have in my green box is my du. Right there. Okay, we okay here? Now, this is a very simple integral for us to do, right? Because now we have this in terms of u, so we can integrate in terms of u, right? So to integrate u squared, we just increase the exponent by 1 and divide out front by 1/3. Or, well, divide out front by 3, which gives us 1/3. What else should I put with it? I need a plus c, because this is indefinite integration, and when I integrate and I don't have my limits over here, I have to put the plus c on the end. Yes? Yes, because it would be possible on this for you to expand all of that out. Yes. Some problems we're going to look at are not even going to be possible for you to expand. It would be possible on this for you to expand everything, distribute that 2x. Yes, so that's a good point. You could do this a different way. It's going to depend a lot on like what your answer choices look like as well, because if you do that, your answer is going to be expanded out. If the answer choices are all factored, that makes it even harder to go back to. So most of the time when we see one like this, we're going to approach it this way instead of expanding it. There. Now, we're not quite done because we don't want u's in our problem. What we're going to do is that u, it equals x squared plus 1, so we're just going to plug it back in. 1/3 x squared plus 1 to the 3rd power plus c. And that will be our answer. There are some problems that we'll get to where it's kind of hard to tell. So you have to have this du to integrate. So like if maybe say that we just, on this problem it's kind of like you've got something being raised to another power, so the inside is probably your u. But let's say that we chose something else, like maybe only the, or maybe we did x squared plus 1 to the 2nd power, right? So when we took the derivative, it would not be there, right? We would have like too much, and you can't add in anything except for like coefficients. So you should always have that derivative there. So like if you take the derivative and it's not here, then that can be a sign that you've chosen the wrong thing at the beginning. Which we will be spending like 4 days on these. They will get a little harder each day. So it'll be fairly obvious on these, like you'll have something inside of a square root or something inside of a power. It'll get a little harder to tell.
Why did you
When we integrate, it is not mathematically correct to say this, but let's think about just like integrating something really easy, like 3x squared, like what we've been doing so far. There was always a dx there. So when you integrate, you're going to raise that exponent by 1. You're going to divide out front by that exponent, so that just give you x to the third. And like we never put a dx there with that either, right? So what's happening, it is mathematically incorrect to say this, but it is helpful to think it. That dx kind of gets replaced by your plus c. Mathematically, that's not what's happening. That d is telling you that you're integrating with respect to that variable, which means when you go backwards, it's not necessary to put it there. But if you kind of think of it as the dx gets replaced by the c, that'll sort of help keep things straight. So like right here, that du becomes that plus c, more or less. I mean, if you think of it that way, you'll get the answers right. If you try to explain it to a PhD math professor when you get in college that way, they might question you, but just don't go down that road. That's what I would suggest. All right, so let's look at example 2. We've got the integral from the integral of 5 cosine of 5x dx. All right, so what do you guys think may possibly be the u here? If. All right, so I'm going to go down, it's not going to be, but let's go down this rabbit hole. If my u is the 5 cosine, it'd have to be of 5x, right? Because you can't have just like 5 cosine, it's got to be of something. If I take the derivative of cosine, what do I get? Negative sine. I'd get negative 5 sine of 5x, and then I'd have to multiply by 5. Do you see a sine anywhere? Where? In the original problem. That can be my du. No. There is no sign in that original problem. So you have picked too much because we can't just like add a sign in, right? We can't put it there. The du would not be there. So we can't do that. So that won't work. Think smaller.
5x.
It's the 5x. Okay? It's this what's inside of the parentheses right here. That is your u. Okay? So u equals 5x. What would we get if we took the derivative of that? Just 5. So you would have du over dx equals just 5. And then again, we just want the du. We don't want the du over dx. So we'd multiply both sides by dx. So du would be 5 dx. Is that there? Pretty much, right? It's not all together, but we could rewrite it if we wanted to. Would it be okay to do this? Cosine of 5x times 5 dx. Is it okay to multiply by 5 at the end like that? It's all multiplied, so you can do it in any order, right? So if we look at this, that 5x right there is my u, and the 5 dx, that's my du. So if we substitute in with our u's, we're going to have cosine of u times the 5 dx is my d. And when you substitute in with that u, it should simplify to something you're able to take the integral of, either with simple trig integrals or the power rule, right? So when we integrate cosine u, what do we get? Not negative. It's just sine of u. And the du turns into a plus c for us. Yeah, your signs are backwards when you're integrating. Yeah. The derivative of cosine is negative sign. The integral of cosine is positive sign. Okay? And then last step here is just to plug your your u back in. So you would have sine of 5x plus c. That would be your answer. All right, questions? All right, let's do some more. I think the best way to get this figured out is just to do several. Here's our next one. Go ahead and copy that one down. All right, what are you guys thinking for the u? I think it's probably x squared plus 1. All right, I think that's probably our u. So, if u is x squared plus 1, what's du going to be? Not quite. 2x dx. Is it okay with you guys if I do this? I know that's going to be du over dx, so I'm going to go ahead and get the 2x, and instead of writing du over dx, I'm going to go ahead and put my dx over here on this side, because that's going to happen every time, right? If you want to do it the long way, you can. All right, do I have 2x dx? No, I'm close, right? Like this x right here, I can move it over here with my dx. In fact, let's do that. Let's write it this way. Let's write it as 2x, or x squared plus 1 squared. We'll put a little bit of space, and I've got my x dx over here, right? But what I really need right here is a 2. I need to have that 2, because it has to match our du exactly. So, what we're going to do, if we have, you cannot add in any variables. So if that x right there was missing, this would be a problem that we're not able to do. Well, or we were not able to do this way. We'd have to expand it and use the power rule. So I've got the variable that I need is already there. I'm missing the 2. So, what can I multiply 2 by so that it would just give me 1/2, right? So if I multiply by 2 on the inside, I can counterbalance that by multiplying by 1/2 on the outside. Overall, I've not really changed anything because 1/2 times 2 is just 1, and multiplying something by 1 does not change its value. We all right with that? I could have multiplied on the 1/2 on the inside, but since it's a coefficient, it could be pulled outside, and it's going to be easier to deal with if it's on the outside there, so I'm going to leave it there. Okay, so we have what we need here. This will be our u, and then 2x dx, that's our du. So we'll have 1/2, we will be integrating u squared du. And so when we integrate, that 1/2 is going to stay on the outside. We're going to have u to the 3rd power. Then we'll have 1/3 up here. And that du becomes a plus c, kind of. So 1/2 times 1/3 will give us 1/6. Let's go ahead and change that u back to our x. So we'll have x squared plus 1 plus c. And that, oh, I'm sorry, forgot it. There we go. Now that's our answer. Whenever you integrate here, you have to increase your exponent by 1 and divide out front by that 3. And what's going to happen, like, it's not that hard to expand this and integrate it using just the power rule, because this is not that difficult to expand, but all the answer choices are going to look like this. And what is difficult is to take whatever you get when you do that and factor it back to this. So you definitely want to use your U substitution for these problems. All right, let's try this one. All right, what do you guys think the U is probably going to be in this problem? Probably 3x minus 5. This inside stuff is usually our U. So U will be 3x minus 5. What will our du be? 3 dx. Do we have a 3 dx? We do not. But could we make a 3 dx? We already got the dx, right? We could just put a 3 over here with it, as long as we multiply out front by what? 1/3. So now, we've got the u right here. We got this stuff right here is our du. We're going to substitute. So we got 1/3 integral of 1 over u squared du. How to integrate 1 over u squared? What do I need to do with that? Let's do negative exponents. It is not a natural log. It would be if it was u to the first power. Derivative integral of 1 over u is natural log. If it's any other power, though, it is going to be just negative exponents. So let's make it negative exponents first. We're going to have u to the negative 2 du. So now we can just use our power rule to integrate here. We'll get the 1/3 sort of hangs out front. We'll get u to the negative 1. And then we'll divide by that negative 1. I mean, you can write that if you want, or just make that 1/3 negative. And that du turns into a plus c, sort of. And so that's going to give us negative 1/3 u to the negative 1 plus c. So negative 1/3 3x minus 5 to negative 1 plus c. There is a good chance they'll move that back down to the bottom. So you get like negative 1 over 3 times 3x minus 5 plus c. Okay, questions? All right, we got one more that we're going to look at. All right, so for this one, first of all, it says solve the differential equation. Only difference here is like you are multiplying both sides by dx right here, so the dx is over on this side, and you're going to have dy equals x plus 2x squared over the square root of x dx, and then you're integrating both sides. So it's essentially just asking you to integrate. That dx is missing because it needs to be multiplied on both sides. What can we use for our u here? If I use the top, I'm going to get 1 plus 4x. That's not anywhere. And I can't add in stuff like that that has variables in it, right? If it's just a coefficient, I can fix that by doing a number and the 1 over that number outside, but I can't do that. Oh, I don't know what we could use for our u here. Any ideas on how we could solve this? What? If I use the entire thing, I will get, like, as a u, I will get a bunch of, like, crazy stuff for the derivatives that I cannot do. We can do love connection, or we can use negative exponents for this. This is not a u substitution problem. And your homework is going to sneak one of these in as well. It's not a u substitution. It's like we were doing earlier. So you're either doing love connection or you're moving that x to the negative 1/2 up to the top. If you're doing your love connection here, you got x to the first over x to the 1/2 plus 2x squared over x to the 1/2, which is going to give you x to the 1/2 plus 2x to the 3/2. And now we just use our power rule for this. So this is x to the 3/2, and then we'll have to divide out front by that 3/2, and then we'll have x to the 5/2, and then we'll have to divide out front by that 5/2, and our dx becomes our plus c. And then so that's going to be 2/3 x to the 3/2 plus, and then here we'll get, let's see, 2 times 2 over 5. If we divide fractions, easy as pie, flip second, multiply. So we'll get 4/5 x to the 5/2 plus c. They might change it back to roots, or they might leave it like that. Either is fine. If it is a definite interval, so if, like, when we were integrating, if we were going from 0 to 4, instead of putting the plus c, we'd have that bracket from 0 to 4, and we would plug in numbers for that. So we don't, if we have a definite interval, and I can't remember if you'll see any on the homework, but we'll see some of those eventually come up. We would not need, I think they're on the later problems, so I don't think you'll see them tonight. All right, so let's see. Let's see if this is what I want to give you. 341. Yeah, I think this is what we'll do. They shouldn't be terribly long problems. So 5 through 23 odd on this. And then we're pretty much just looking at, like, a little bit harder versions of this the rest of the week. We'll have to throw in some trigs, e's, natural logs, all of that stuff. 23.